Okay, welcome back. We're going to pick up where we left off last time. We were learning about thermal energy, and in the last lesson, we talked about how temperature was the average energy of the particles in a substance. Thermal energy is the total potential and kinetic energy of a substance, atoms, and molecules. So because it's the total, okay, it depends on how much of a substance there is. And I said, don't confuse this with mechanical energy, which is the potential and kinetic energy of a system. So in mechanical energy, we're measuring the motion of the parts, like, the motion of the parts of an airplane or the airplane as a whole. In this case, we're looking at the energy of the individual atoms. Because it's the total energy of the atoms, the more of the substance, or the more atoms and molecules, the greater the total. You can also make the atoms move more to increase thermal energy, which is increasing the temperature. So if either the amount of the substance increases or the temperature increases, then the thermal energy increases. So I put in here thermal energy increases as temperature increases. Thermal energy also increases as mass increases. So if you think about the amount of thermal energy in a glass of water that would be at room temperature, and then the whole ocean is absorbing thermal energy from the sun. So as millions of square miles of ocean are absorbing energy from the sun every day. So it has an incredible amount of energy stored in it. And we're going to take a look at this short clip on the basics of physics, exploring heat and temperature and heat. Okay, in this segment, we're going to take a look at the difference between heat and temperature. You should recall that heat is a measure of the total kinetic and potential energy of the particles in a substance, whereas temperature is a measure of the average energy. So we're going to review that heat depends on the amount of a substance and temperature does not.
The words temperature and heat are often used to mean the same thing. Actually, they are related, but they don't mean the same thing. Temperature is used to measure how hot or cold an object is. Objects with the same temperature can give off different amounts of heat. Think about this situation. Here are 3 beakers with different amounts of water in each.
Okay, now think about this, okay? And think about the total number of particles in the 3 beakers as he explains.
Temperature is exactly the same in each beaker. The question for you is, which beaker contains the greatest amount of heat energy?
Now imagine if this water in these beakers was all right at boiling. Which one would have the greatest amount of stored heat? They would all be at the same temperature because they'd all be right at boiling, right at about 100 degrees Celsius. But obviously, the one that has the largest amount of water would have the most amount of heat in it. Okay? If you think about putting it on the stove to warm it, it would have taken the longest time to warm up because it would have taken more heat from the burner to get it to that temperature.
Well, the largest beaker contains the greatest amount of heat energy. Imagine if the temperature had been much higher, such as boiling. If the water were to spill on you, the large beaker would hurt the worst because it has a greater mass of water. And therefore, even though the temperature is the same in all 3 beakers, the larger one has more heat. Heat is determined by the temperature and the amount of the substance. Temperature is measured with a thermometer, which is usually a hollow tube with either mercury or colored alcohol in it. The fluid will move up or down the tube, depending upon the temperature of the substance being measured.
This is another example of thermal expansion. As the particles of the alcohol or the mercury inside the glass tube heat up, they move faster. As they move faster, they take up more space. As they take up more space, it expands up the tube.
It works like this. All matter is made up of atoms and molecules that are in constant motion. We can't see this motion because the atoms and molecules are so very small. A piece of paper is 1,000,000 atoms thick. When matter is heated, the atoms or molecules move faster with greater strength. They bounce around more and are more active. When the thermometer touches the object, the motion of the object's molecules is transferred to the molecules of the thermometer fluid. The fluid then either expands because the molecules are moving faster, or the fluid contracts because the molecules are moving slower than before. When the fluid expands, it moves up the thermometer and registers a high temperature. The motion of atoms and molecules in matter is called kinetic energy. So temperature measures the average kinetic energy of a.
So notice how the kinetic energy of the solids is the least. The particles are moving around the least. And in the liquid, they're moving around more. And finally, in the gas, they're moving around more. So like when they strike the edge of the thermometer, the gas particles have more energy to transfer to the liquid in the thermometer. That causes those particles to gain energy. And when they gain energy, they move faster. And when they move faster, they take up more space and they expand up the thermometer. So when we say that it's measuring the average kinetic energy, which is temperature, that's what they're talking about.
Substance.
All right, now I want to take a look at this picture that I made. And let's say you fill both of these pans with water from the faucet. Okay, they're at the same temperature. You put them on two identical burners on the stove. And you put them both on high. So the amount of energy coming out of the stove going into the water is the same. It's coming out at the same rate. Okay, so you can think of that burner adding thermal energy to the water in both of these containers. So I put in here the burners add heat or thermal energy to each pan at the same rate. Predict which one do you think will boil first and why? Okay, well, this is where we're talking about thermal energy increases as temperature increases. So both of them are going to be increasing in temperature. But thermal energy also increases as mass increases. And you should know, it's common sense that the pan with just a little bit of water will boil first. So the small one is going to come to a boil first. And why? Since there's less water, it will take less energy for the stove to bring that water to a boil. Okay, so this is where thermal energy depends on mass. So as the water gains energy, this water needs to gain a whole lot more total energy to bring the average energy or the temperature of the particles to the same boiling as the small one. When they both get to boiling, what will the temperature be? Well, water boils at 100 degrees Celsius or 200 degrees Fahrenheit, and they'll both be at the same temperature. So when they finally do come to boiling, they're going to have the same average kinetic energy. They're going to have the same temperature. But the big one is going to have more thermal energy stored in it because there's so much more water. So I put in here the last thing. Do they have the same amount of thermal energy at that point? No. The large pot will have much more heat or thermal energy from the stove stored in the water. Okay, and that's why it took so much longer for it to heat to a boil, because the two things that thermal energy depends on is mass and temperature. Well, they both reach the same temperature, which is boiling. But this one has so much more water. It took much more heat from the stove, and that heat is stored in all this water. Okay, and then heat, which is the flow of thermal energy, always flows from high to low. And as a matter of fact, in science, everything always moves from high to low. So in this case, thermal energy moves from high temperatures to low temperatures, or hot to cold. When heat flows into an object, the temperature raises. It's called positive temperature change. And notice we always start when heat flows. When heat flows out of an object, the temperature change decreases. This temperature change is negative. Okay. I want you to think, and this is what idea of everything flows from high to low. Let's say I had this special graduated cylinder, and I had water on this side and water on this side, and something blocking them. Okay. If I remove this barrier, what would you expect to happen? Would you expect the water to go from low to high, or would you expect the water to flow from high to low? Everything flows from high to low. So after I remove the barrier, okay, the water on the high side would go over to the low side, and then they would become equal. Now, if this is hot and this is cold, the energy from the hot is going to try and move to where the place where it is low, because these particles have a lot of energy. They're moving. So in the summertime, if somebody asks you, are you trying to keep, in your air conditioning your house, are you trying to keep the cold in or the hot out? Well, you're trying to keep the hot out. The air outside the house, those particles have a lot of kinetic energy. They want to bump into the particles in the house and transfer their energy in. In the wintertime, when it's warm inside and cold outside, are you trying to keep the cold out or the heat in? You're trying to keep the heat in. The air inside the house has more energy. It's high. It wants to transfer its energy to outside where it's low. So when we say heat always flows from hot to cold, everything flows from high to low. We're going to take a look at this short clip on the movement of heat. Okay, in this segment, we're going to take a look at how heat moves from warm to cold. Okay, and the basic idea is that the particles in something that are cold are not moving very fast. So they don't transfer energy to other things. They have nothing to give up because they have very little energy. The thing that's warm, its particles are moving really fast, and its particles can bump into the cold one and transfer energy to them. So things always flow from high to low. So temperature is going to flow from warm to cold, or high temperatures to low temperatures.
Heat moves from warm areas to cold areas. We use insulation in our homes to keep the heat in, not the cold.
Okay, so the particles out here where it's really cold outside don't have very much energy. They're not going to transfer anything to the particles in the house. Particles in the house have a lot of energy. So the warm air inside the house is going to bump into the wall, and it's going to, conduct a little bit through the wall, and it's the fast moving particles of the house are going to transfer their energy to the outside. So the heat is going to be flowing from inside the house to outside the house, which is, we put the insulation there to stop the flow of heat out of the house. So really you're trying to keep the heat in, not the cold out.
The heat wants to move to the colder outside during winter, so we try to cut down on heat loss. Something that slows down the movement of heat is called an insulator. Certain materials, such as wool, plastic, and wood, are poor conductors of heat, so they make good insulators. Fiberglass is used in attics and walls of homes to slow down the movement of heat from the warm interior to the cold outside. Snow is a good insulator. That's why the Inuits build their winter igloos out of snow. A thermos bottle is a perfect example of a device that is designed to slow down all three forms of heat transfer: conduction, convection, and radiation. The thermos bottle is made of 2 layers of glass that are separated by a vacuum, which is the absence of air or other gases.
Okay, so where they have this vacuum area, there's no particles. So no particles would stop conduction and convection, because both of those heat transfers require particles. Okay, the shiny layer is going to reflect the radiant energy, so that is going to try to stop the third heat transfer. So it'll be working on all 3 heat transfers: conduction, convection.
Glass is a poor conductor of heat. We can demonstrate that glass is a poor conductor with this experiment. We will boil water in this test tube while holding the other end of the test tube. The vacuum is a wonderful insulator because there are no particles for the heat to vibrate. The glass is silvered so that it reflects radiated heat back to the inner container. When something hot is poured into the thermos, it will stay hot for hours.
I want to take a look at this short clip on measuring heat and see how heat is measured in different objects Okay, we're going to take a look at how heat is measured.
Heat is not measured with a thermometer and in degrees. There are different units used to measure heat energy. One is called the calorie. The calorie is the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius.
Now remember, again, we said heat depends on the amount of a substance. So the definition of a calorie is it's the amount of energy needed to raise the temperature of 1 gram of water 1 degree. So if you had 100 grams of water and you wanted to raise it 1 degree, it would take 100 calories. So the amount of heat is dependent on how much material there is.
Food energy is measured with this unit. The unit used to rate food is actually a kilocalorie, which is 1,000 calories. Notice that when you look up the calories on a package of an item of food, the word calories is shown with a capital C. This is to indicate that it is 1,000 calories. This can of vegetable soup indicates that it contains 90 calories of energy, which are released when the soup is eaten and digested. People get the energy their bodies require from the food they eat. A special instrument is used to measure calories.
This is called a calorimeter. So they dehydrate the food and they put it inside here, and it's burned to see how much energy it releases. So you find the temperature of the water before, and then the food is burned. You find the temperature of the water after. That's how much heat went from the food into the water. So that's how many calories were in the food.
It is called a calorimeter. Basically, it is made of 2 chambers, one inside the other. The outer chamber holds water. The inner chamber is where the food sample is burned. The temperature of the water in the outer chamber is measured before and after the sample is burned. Then the difference in temperature is multiplied by the amount of water to determine the calories of heat given off. The standard unit used to measure energy is the joule. Energy is...
Now remember, we said work and energy were related, and joule was the unit for work. It was the energy necessary to raise 1 Newton, 1 meter. So that's why they're showing this kid lifting weights, because it's really should be reminding us that energy and work are related.
Is the ability to do work. Work is measured by multiplying force by the distance it is exerted. In the scientific community, this means newtons of force times the distance measured in meters. The basic unit for work is the joule, which is 1 newton of force exerted over 1 meter. 1 joule equals 1 newton meter. Since work and energy are closely related, the joule is used to measure energy as well. 1 calorie equals 4.18 joules. Another unit used to measure heat energy is the British Thermal Unit, or BTU for short. This unit is defined as the amount of heat energy needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. This unit is often used to measure the energy output of heating and cooling systems such as furnaces, ovens, refrigerators, and air conditioners. This furnace is rated at 124,000 BTU per hour. The BTU is primarily used in the United States, as the joule is used throughout the rest of the world. Both the joule and BTU can be used to compare the energy output of various fuels. For instance, a gallon of gasoline equals 124 BTUs. A gallon of diesel fuel equals 139 BTUs. 1 gallon of propane equals 91 BTUs. Prices can be determined for each of those fuels, and then the most efficient fuel can be determined.
Now, I want you to answer these questions on your own. We're going to stop here, and when we come back, we're going to pick up. I hope you're having a great day, and we'll see you next time.